just because whilst we did do first principles on Monday, I'm also fully aware of the fact that we only got through like 3 examples, but it's because it takes so long to do a first principle question. So I'm going to put this up here. I'm going to give you 5 minutes to give this a try. If you, don't know where it's going with that. If you're feeling stuck, please just ask me on the group what's what. I'm going to write the steps that we wrote down on Monday on the side in case you have forgotten or in case you just need a little bit of guidance. But remember, grade 12, you do not use first principles. You do not use this method unless the question says differentiate using first principles. You will always be asked a first principle question, so you can guarantee that you're going to be asked the first principle question or to differentiate using first principles. But today we're going to learn some of the rules. Use the rules. All right. So unless it says using first principles, you don't use first principles. Okay. Like I say, excuse my childish handwriting. I have a solution. It's just a solution I need to get used to. So just work with me. Alrighty. So while you're trying, your first step was to determine your f of x plus h expression. Your second step was to sub it into your formula. Ooh. Like I said, the handwriting will get better. Okay, and this formula is obviously this bad boy over here. Your third step was to factorize. You know, I said it would get better. It's not getting better. And then your fourth step is to consider that limit of h is to 0. All right. So again, I apologize for the handwriting. I will get better at it. We'll get there, but it's okay for now. Right. So 5 minutes. Give this one a try, and then we'll have a look. And then we're going to look at the shortcuts. What's really nice. Sorry. What's really nice with the shortcuts is even when you're asked to do first principles, because you will have learned the rules and the shortcut rules, you can look at a first principle question like this, and you can automatically in your head do the differentiation so that you know what your answer should be, so you can double check yourself. So for example, I already know what this answer should be. Obviously, I've done the question, but if I hadn't done the question, I would look at this, I would know what my answer needs to be. And so when I do my first principles, I know what I'm aiming towards. All right, so let's give this a try. Like I say, a few more minutes, and then we'll have a look, and then we'll look at the rules that we can now use if we're not asked to use first principles. Alrighty, great tools. Let's have a see. Okay, so again, excuse the handwriting that's going to ensue in this lesson, but we're going to be fine. So remember, first thing is you want to go and work out your f of x plus h. So this is what we're doing over here. We're doing the first step. We are substituting in place of these x's in your expression. We are substituting in x plus h, and we are working out what f of x plus h is. So what you just need to bear in mind is, and I said this to you on Monday's lesson, and if I didn't, then I said it, I don't know, in my head. But anytime you're working out f of x plus h, remember this bracket represents x. So everywhere you see an x in your expression, you have to replace it. So that's why we've got the minus x plus h squared and then the plus 4 times x plus h. So obviously we're going to distribute, and then you're going to expand your bracket squared. Remember, you do have that -1 coefficient, so you do also need to distribute that better than whatever I was just drawing there into your bracket. And once you have done all of the distribution and stuff, you get an expression. Now, always try or always see if it is possible for you to simplify this expression. So check if there's like terms, etc., etc. Sometimes, like in this case, there isn't, and we can't do anything with it, and so we move on from it. But if you can simplify, do, just because it's going to make your life easier. Right, then we move on to step 2, which is substituting into f of x, and this is what we do here. Remember, this notation, this lim h is to 0, has to be here for every single step until you have completely simplified, substituted in your 0 value for h, and you've gotten your derivative. Only in your last step can you drop the lim is h to 0, okay? Reason being is because all of these steps that we've done prior to has yet to take into account that h equals 0 value that we need to do in step 4. And it's only that very, very last step that we are able to then actually work out what our derivative is. Okay, so we substitute in. Remember, if we go back up to our formula over here, it's f of x plus h minus f of x. So when we go and substitute in, again, you have a negative here that you need to take into account, and you're going to distribute into your bracket. I've also said this to you, I said this to you on Monday's lesson. Please also bear in mind that these terms in this bracket, once you've distributed the negative in, should cancel with other terms in your f of x expression. So if we have a look here, let's get a different color going here. So if we have a look here, when we distribute in the negative, it becomes positive x squared, so that cancels with the negative x squared. When we distribute in the negative, it becomes negative 4x, so that cancels with the positive 4x. Those two terms of f of x should cancel. Okay, so if we carry on, we can now see that what we have is minus 2xh minus h squared plus 4h. Our third step is to then factorize, and remember, factorizing, we take h out as our common factor. And once we do that, we are then able to substitute or replace h with 0, and we're able to find our derivative. Right, so first principles, like I say, you only do them if you are asked to do the derivative or to differentiate using first principles. Otherwise, it's time consuming. Don't do it. Right, you will get a question like this. You're guaranteed 5 marks. So be sure that you can bank those 5 marks. It's a silly 5 marks to lose, because really all this is algebra. Okay, I'm fully aware of the fact that there is some slightly questionable writing going on here. So let's just take off a little bit so that we can still see what's going on. Right, so you can have a screenshot of this example. I think that's a fair amount to have taken off. And then we're going to have a look at the rules that we can use to now apply when we try and differentiate. Because again, take the shortcut where you can. Right, guys, hopefully the handwriting will get better throughout the lesson. We'll see. Okay, if you can't read something, you just let me know. Okie dokes. Right, so when we start to learn these rules for differentiation, there's a few things we first need to bear in mind. So there's a few things that we need to sort out before we just start applying rules. So the first thing that we need to be mindful of is the fact that the format in which we write our answer is incredibly important. And because we are working with expressions that have degrees higher than 1 most of the time, we need to be mindful of our exponent laws. Okay, now these you've been doing since grade 8, so I'm not going to go through them. I'll leave it up here for you to take a screenshot. But understanding your exponent laws is incredibly important, right? The ones that are, I'm not going to say most important, but the ones that will come up most of the time is the idea of a negative exponent. So understanding that if you have got a variable in your denominator and you want to get it out of the denominator, you would introduce a negative exponent. I'll explain why that is in a second. The second one that's also going to be quite important is these two down at the bottom that have to deal with rational exponents. Okay, so those exponent laws are very important for us. We need to know them, but like I say, you've been doing them for the past 4 years, you know them. Okay, so take a quick screenshot if you want of this. Otherwise, I'm going to move on to talk about why this is important. Right, so this is important because the way we write our expression before we start differentiating is incredibly important. The rules for differentiation rely on a specific format of each term in our expression, and it needs to be written in that specific format. Okay, so the format that we use is as follows here. So obviously that's just a bunch of symbols to us right now. Let's just understand what this format is. Maybe, maybe not. Yeah, sorry, it'd help if I had the pen in the right way. So you first want to have your sign. So what I mean by that is it positive or negative? And I'll give you an example in a second. Then we want to write the number. Now the number means the coefficient. So if your variable has a coefficient, we want to write that number. I'm just going to put coefficient under here. We then want to write whatever the variable is. We work 80% of the time with x, but sometimes it can be another variable. And then we want to write our exponent. Okay, so we never want to have a situation like, let's say, for example, something like this. I don't want a fraction. I want my variable to be on the same level, so in the numerator with the rest of my values. And so this is where the idea of that negative exponent becomes very important for us. So we need to write our format correctly. Okay, so basically, just like a little, I don't know how to say this, basically like a little summary. No variables in your denominator. Okay, I'm just going to abbreviate. Denominator. No square roots or surds. Because like I say, you want an exponent, not a root. And we know that we can write surds as exponents. And the next thing that we want in terms of our format is simplified. Okay, and I'll talk more about this as we go along with this. So simplified could mean if you had 2/4, simplify that to a half. If you had a fraction where you had a binomial in your denominator and you can factorize the numerator, factorize first and simplify. So you always want to be working with a simplified expression when it comes to these sorts of questions. All right, but let's just have a look at actually putting expressions in the correct format that we want before we jump into actual differentiation. Okay, so this first one that we have over here, my issue is this x in the denominator. Now, I have got no issue with the half. Okay, the half is absolutely fine as it is. That's cool. What I do have an issue with is this x in the denominator. So what I want to do is I want to bring it up into my numerator, but I know that that means that I then have an exponent of -3. What I want you to bear in mind is that it is the same thing if you had written 1x to the power -3 over 2. So if you had written it as a combined numerator and then denominator. Now, the reason I wouldn't do that is going back to the format that we want. It will also just make it easier when we start applying our rules. I don't care if you write it like this, personally. If you can understand how to apply the rules using this, go for it. But we want the sign first. So it was a positive. Obviously, we don't write positive. Then the coefficient, half. Then the variable x, and then whatever the exponent is. Our exponent of -3 implies that it was originally in our denominator. We just don't want to write it in our denominator. So we want to write it in this first format that we have over here. Okay. So based on what I've just said about the whole fraction situation, if we look at B, this is very much what I was saying now. I do not want my variable sitting in the numerator with the 3. Okay. I want the sign, then the number, then the variable next to it. So we basically just separate out our fractions. Okay, that's a 3. Let's try that again. So we separate our numerators. So 3 over 7, there's the number. And then we write the x to the power 5. Again, there's nothing wrong with this format. Please understand that these formats that we're given initially, there's nothing wrong with the formats. They are just not the formats most useful or most conducive when we have to now start applying our differentiation rules. Okay, if we move over to C, this is an example where I said we always want to simplify. So I'm just going to go over a little bit here. I need to distribute this exponent into this bracket so that I have a simplified denominator. So this will be 1 over 25x squared. Let's just fix that. And then again, I don't want that variable in the denominator. So I will write this as 1 over 25. And then next to it, x to the -2. -2 because it comes out of the denominator, and next to my coefficient because that's the format that is most useful to me. Again, there is nothing wrong with 1 over 25x squared, but it's not the format that is most useful to us for differentiation. Right, when we get to question D, the issue with surds is basically the fact that I don't want any surds, like I wrote over here. So this is now where your knowledge of exponent laws really becomes important. We really only do this in grade 11, and it's a very small section in grade 11. So I do understand if surds is not something you're super comfortable with. My advice is, A, don't stress, but B, maybe go back to your grade 11 notes and just practice those exponent and surds just to feel a little more confident with it. Right, so the first thing is we want to simplify the situation in our denominator. So I'm going to leave the 2 in the numerator because I don't have an issue with that right now. But now I want to deal with the surd. Now, when we deal with the surd, there's a way that I like to remember surds because honestly, for me, the rules are quite abstract. So the way we do this is, firstly, when you have got a root, so we've got cube root 27x to the power 9. Those are 2 factors that I have in my, or underneath my cube root. What we need to remember is that according to my rules, when you've got multiple factors, you apply the root to each factor. So this would be the cube root of 27 times the cube root of x to the power 9, and you deal with them separately. So the cube root of 27 is 3, and the cube root of x to the power 9, now this is where our exponent laws come in. According to our exponent laws, what we do is we take the variable underneath our square root or our cube root or our fourth root, whatever it is, and we write the exponent as a fraction. Now, the fraction is written as follows. You take the exponent that is attached to the variable underneath the root and you put it in your numerator. And in your denominator, that is the root that you are working with. So this would be 9 over 3. Now, obviously, we can simplify 9 over 3 to then just x cubed as my simplified expression. But if you're going to convert from surd to exponent, it is exponent of the variable underneath your square root or your cube root or whatever over the root. Right, so just to reiterate this with another example that doesn't, for example, simplify. Let's say, for example, you had the square root of x cubed, and you needed to write that as a rational exponent. Take the variable underneath the root, so x, it's been square rooted, so that is your denominator, And then 3, the exponent that is attached to the variable under the root, is your numerator. Now, okay, this might be very stupid, and you can laugh at me if you want. I've got no issue with that. I remember it as a flower. Okay, I'm probably not going to be able to draw a flower, but we'll just roll with it. Oh, beautiful flower. A flower, because a flower has roots at the bottom. So the root goes at the bottom. Right, like I said, if that's helpful to you, awesome. If it's not, you do you. But that's how we deal with surds. So if we go back to our question, we now need to deal with the 27x to the power 9 being cube rooted. I have actually already written down the answer, so we know what it is, 3x cubed. And now we deal with the fact that we have the variable in the denominator. So we would write our 2/3 number, variable, and because it's coming out of the denominator into the numerator, it becomes a negative exponent. All right, so the notation of your expressions that you're working with when you derive is incredibly important, right? It makes your life a lot easier when it comes to applying your differentiation rules. Right, so let's screenshot those 4, and then you're going to try, you can see on the side there, you're going to try some by yourselves. Right, I just want you to try E and F. What I will do is I'll leave C and D there so you can still see them, just so you can see what we were doing. But I want you to try E and F for me. I want you to write it in the correct format, the sign, then the number, then the variable with its relevant exponent. And I am actually going to change that to a -3 over the 4th root of x cubed. Right, let's try it. I'm going to give you 2 minutes, and then we'll have a look at what we need to simplify that to. Remember, if you need help or if you're not too sure, if you have questions, please just ask. You can pop it in the chat. You can unmute yourself, but just let me know if you need help. Okay, cool. So there's a question of how do we go from root 27 to 3. So just bear in mind it is a cube root of 27. And so if we cube root 27, remember 3 times 3 is 9, times 3 is 27. So the cube root of 27 is then 3. All right, so it is a cube root, so just be careful there. And whenever you cube root something, it's the same as square root. But if we specifically look at cube rooting, it's asking you what 3 identical values you multiply together to get the number underneath the root. So the 3 identical numbers we multiply together to get 27 is 3. Hence, the cube root of 27 is 3. All right, question to explain question D again. Absolutely. I'm just going to take off my work of art and do it again, because I think if I try and annotate this, no one will understand what's going on. So let's have a look. If you're still busy with E and F, that's cool. I'm just going to explain D again, and then we'll have a look at E and F. Okay, so the first issue that I have in D is the fact that I've got a square root, or surd rather. Let's not say a square root, also because it's not a square root, it's a cube root. So I'm going to deal with that first. So let's actually go and sort of block that off and say that's what we're going to deal with first. Right. So So we've got the cube root of 27x to the power 9. Now, whenever you've got multiple factors that are being square rooted, cube rooted, whatever, are underneath some sort of root, what we need to remember is that we can go and say the cube root of each of those factors. So the cube root of 27 times the cube root of x to the power 9. Now, obviously, if you can do that all in one go, that's absolutely fine. Do it. But whenever you are square rooting or cube rooting multiple factors, you just cube or square root each factor and you will get your answer. Okay, so cube root of 27, you can just do this on your calculator. But this is essentially asking what 3 identical numbers do you multiply together to get 27? 3 times 3 is 9. 9 times 3, 27. So the cube root of 27 is 3. And then we get to the cube root of a variable. Now, this will work obviously with any variable, but let's have a look at this. Right, maybe I'll overcomplicate it also with the flower and all of this stuff. Basically, what you do is you take the variable to its exponent and you just divide it by the root. If you want to write that exponent as a fraction, go for it. I'll show you an example now where we would need to. But all you do is you divide this exponent under by the exponent outside. So 9 divided by 3 gives me x to the power 3. So the cube root of 27x to the power 9 is 3x cubed. Now we can go back and we can go and simplify further. So this fraction becomes 2 over 3x cubed because we've simplified our denominator. And remember, we don't want that variable in the denominator. So we write it as 2 over 3. So 2 over 3 because that's my coefficient over there. And we want to take the x out of the denominator and put it into the numerator. So that exponent has to become negative. And now it's in the format that I want it to be in. Right, just quickly, if we go back to this whole x to the power 9 divided by 3 situation. Let's say, for example, you had the square root of x to the power 5. You do exactly the same thing. You take x to the power of the exponent it is raised to, and you divide it by the root. You would divide by 2. Now, obviously, 5 divided by 2, you can just write as a fraction. So this would be x to the power 5 over 2 is your rational exponent. So all you do when you have got surds that you're working with is you take the exponent under and you divide it by the root. That's it. Right, let me know if that makes a bit more sense. And then I'm going to have a quick look at E and F so we can get to our rules. Okay. Connie?
Ma'am, can I ask a question? So if we had, like, next to the 2, if we had an x to the power of 4 and we wanted to move the other x to the power of 3 up, what would we do?
Okay, so for example, if there had been an x to the power 4 in the beginning, like that.
Yes, ma'am.
Okay, cool, good question. So if we did that, what I'm actually going to do is this for now, and we'll go here. All right, so I don't know why I wrote that as a -3. Sorry, that should not be -3 because... Okay, let me just fix that. Right, so we're currently sitting with this situation. We want to bring that exponent up into our numerator. So we can do that. Let's just carry on over here. You would bring it up into your numerator, but what would happen is that x to the power 4 would still be there, but now you have got the x to the -3. Now, when you bring from a division into your numerator or from denominator into numerator, the operation between whatever's in your numerator and this thing that you've moved up is multiplication. So this would be over 3. And now this is where we would apply our exponent laws. When we multiply with the same base, you add the exponents. So this would become 2 to the power, no, let's try that again, 2x to the power 4 plus -3, so 4 minus 3, which is then just 1 over 3. And then we would separate out our fraction and go like that. So that's a really nice question in terms of if you had variables in both your numerator and denominator, you can then continue to apply your exponent laws and simplify further. Does that help? Okay, cool. Awesome. Good question. I actually have never even thought to introduce an example like that. Really good, nice question, Connie. Thank you. All right, guys, let's have a quick look at E and F. So E, again, the issue here is the surge, so the square root. So if we deal with that square root first, we would have x to the power -8 divided by 2. Remember, you just take the exponent under and you divide it by the root, in this case 2, and that simplifies to x to the -4. So what we now have in our fraction is 1 over x to the -4. I don't like the variable in the denominator, so I bring it up to the numerator, which means I get x to the power +4. If you want to write the 1 there, that's absolutely fine. You don't have to, but you can. For question F, again, my issue is the surd in the denominator. So what we're going to do is apply the rule exactly as we had earlier. X to the power 3 divided by the root, so divided by 4. And so we simplify to x to the power 3 over 4. That is in my denominator, so we'll see what happens now. So we have got -3 over x to the power 3 over 4. Again, I don't like that in my denominator. I need to move it to the numerator. So sign, number, so the 3, and then x to the power -3 over 4. And I've got it in my format that I want. Right, so I'm not saying these don't come up often. I mean, they don't, actually. Realistically, they don't come up often. These types of questions, so in your exams, you generally get a first question, differentiate using first principles. And then the next question will be testing whether or not you understand the formatting. So can you put the format correct? But honestly, guys, it's maybe 2 or 3 questions, and they won't be a huge amount of marks, maybe like 3 marks, right? Not like massive. And so it's really just testing your formatting. These ones with the square roots and all of that, we don't work with a whole lot, right? So you will get a question or 2, but not a lot of them. But it is important to understand how to correct your format, because like I said in Monday's lesson, format and notation is incredibly important in calculus. Alrighty, so excuse me, let's screenshot E and F, and then let's have a look at how we can now take the correct format and differentiate it using some shortcut differentiation rules. And again, just keep asking questions if you're not sure. Toriso, I'm so sorry. I only saw your message now. Do you need me to explain D again, or you good? Oh, no, never mind. Please ignore me. Just, ignore me. It's all fine. Okay. Right. So again, notation in calculus differentiation is incredibly important. We have already looked at this first type of differentiation. So if you are given your expression in the form of f of x equals, we know that the derivative is represented by f dash x. Okay, so we show we've taken the derivative by using that f dash x. There are other ways that we can ask the derivative though. If I give you your expression in the form of y equals, so you can see here, let's say, for example, y equals 5x squared plus 3x. The way we represent that derivative is to say the derivative of y basically in terms of x. So we say dy over d of x. And those d's essentially in front of the y and the x represent your derivative. Now think about it. Derivative represents gradient. Gradient is the change in y over change in x. So y in the numerator, x in the denominator. The last way that we can represent a derivative is to say the derivative, so d, in terms of x of a function. So the derivative in terms of x of 5x squared plus 3x. And then we just go and write the answer. You drop, so here you can see you drop the dx notation once you have found the derivative. this d of x, so this little d in the subscript x, represents or says that we're finding the derivative. Once you've got the derivative, you drop it, you leave it, that is the derivative. These are the two that we work with. I don't know what on earth that was trying to be. These are the two that we work with the most. I'm not saying that you can't get question 3. You definitely can in questions where we're testing whether you understand notation and you understand formatting. But we definitely work with 1 and 2 more often. All right, but I don't want you to stress too much about this. As we go through examples, I will do the correct notation and I will remind you so you can see. Take a screenshot of it so that you have it, but let's have a look at some examples. And like I say, as I go through, you'll see the notation and you'll see how we go about writing it, because it's all very well me saying this, but we actually need to put it into practice. Cool. Right, so now we get to the actual rules of differentiating. We're going to start with just some basics, and then we'll do the more complex ones on Monday. The first basic rule or shortcut rule when we find a derivative is that the derivative of a constant is always equal to 0. Okay, so let's try to do better. The derivative of a constant always equal to 0. So if you were asked to find the derivative of f of x equals k, so I'll give you an example now, f of x equals 10, that 10 is a constant. There's no variable attached to it. The derivative is 0. So that will always be the case. If you wanted to go and try and do this by first principles, awesome, you will get 0. The second rule is our power rule. Okay, so the power rule says to us, and I'm going to probably write this out for you now, is that if we are given the expression x to the power n, we multiply the coefficient by the exponent, and then we subtract 1 from the exponent. So if we have a look at this example, my original expression, x to the power 10. What I do here in order to find the derivative, we'll get there in the end, to find the derivative is, I take this exponent of 10, and I multiply it with my coefficient. Now remember, my coefficient in front of that x is 1. So 10 times 1 is 10. And then I subtract 1 from the exponent, and I get 9. Now let's quickly scroll up, and we'll do some examples, but let's quickly scroll up to this first principle one that I gave you. If we apply those two rules that we've just had a look at, first rule is take the exponent and multiply it by your coefficient. So -1 times 2 is -2. We then have our variable, and we subtract 1 from that exponent. So 2 minus 1 is just x to the power 1. Then we move on to the next term, and we do exactly the same thing. This x has an exponent of 1. So 1 times 4 is still positive 4. And then we subtract 1 from the exponent, which gives us 0. Now remember, anything to the power of 0 is 1. So it just stops at 4. If you look at the answer that we got from our first principles, it's exactly the same. And this is why the shortcut rules are so nice. You eliminate, you eliminate all of this and you get straight to the answer. So the rules here that we need to apply are timesing your coefficient by the exponent and then subtracting 1 from the exponent, as well as any constant would differentiate to 0. It would essentially fall away. Okay, so again, let's take a screenshot of these rules, but let's actually look at some examples and see how we do this. Right, actually, you can take a screenshot in a second because I've put the examples right here. Right, so we've been given f of x is equal to 3x to the power 6. We want the derivative. So f dash x is equal to, we take this exponent and we times it by the coefficient. So 6 times 3 is 18. And then we subtract 1 from the exponent. So x to the power 5. Done. You have found the derivative. If you had to do that using first principles, imagine you would have to substitute an x plus h in place of x and then raise that to the power 6. You're going to be distributing until the cows come home. Differentiation rules make life easy. If we have a look at example 3, again, we want the derivative, but this is now where the formatting becomes very important. Okay, so let's first get the format right. So I'm not doing the derivative yet. That's why I don't have a dash there. I'm just getting the format right. I want the number first, so 1 over 3, and then my variable, so x cubed. Now that my format's correct, I can do my derivative. So now I can introduce my f dash x, and I use the same rules that I was doing earlier. So first thing that I do is I take my exponent and I multiply it by a third. A third multiplied by 3 is actually just 1. And then I subtract 1 from my exponent, leaving me with 1x squared, or obviously just x squared is absolutely fine. If we have a look at example 4, I'll make this a bit smaller for you to screenshot everything now in a second. Again, the formatting is important, but we've also got a new notation that we need to be careful of here. Oops. So determine dy over d of x. This is the derivative. That's all this is saying. Okay, so determine the derivative. Let's spell for a second. So to do this, first let's fix the format. So we're not dealing with the derivative yet, so I'm still going to work with y. Number first, so 3 over 2, and then we're going to bring that x to the power 4 up, so x to the power negative 4. Now I'm going to deal with the derivative. So now I introduce my derivative notation to indicate that I'm now doing the derivative. Right, rules tell me, take the negative 4 and multiply it by the coefficient. Now I'm going to be honest, I don't have a calculator handy, so I'm just going to have to do this quickly on the side. Obviously you use a calculator. So 3 over 2 times negative 4, that gives me negative 6. Okay, so negative 6, x, we subtract 1 from the exponent, so minus 5. You found the derivative. That's it. So these rules make life so much easier when it comes to finding derivatives, because once you understand the rules and once you can apply the rules, it's literally a one-step process. Right, let's look at example 5. Like I say, I'll make it all smaller now for you in a second to take a screenshot. But example 5, I want to show you because what we can see here is that there's multiple terms. So whenever you have multiple terms, you are going to, I'm trying to say differentiate, but you know, each term separately. Got some cursive going at the end there, but we're fine. Right, remember, this is a notation that says determine the derivative in terms of x. The second you start using your rules to find the derivative, you just drop that d of x in the square brackets. So first I want to check, is my format fine? My format is absolutely perfect for all of these. So I'm going to drop that d of x straight away, and I'm just going to go to my derivative. So term 1, 4 times negative 1 is negative 4. And then we subtract 1 in my exponent, so I've got x to the power 3. Move on to the next term. A third x cubed. A third times 3 is then just positive 1. Subtract 1 from your exponent, x squared. Term 3. This exponent is 1, so 1 times negative 2 is negative 2. Subtract 1 from your exponent, you end up with x to the power 0. Now, x to the power 0 is 1. 2 times 1 is still 2. This last term is a constant. Remember, that becomes 0. So it actually just falls away. So your derivative here is minus 4x cubed plus x squared minus 2. That's it. So an expression that actually looks really gross, and if you had to try and do that with first principles, is much, much easier. Yes, it is minus 6. Thank you, Leila. I don't know what I'm doing in life. So negative 24. Thank you. Who knows where I'm at? Okay, there we go. I fixed it. Right, so these rules, as I say, make life so much easier when it comes to determining derivatives. Right, so let's take a screenshot of that so far. There was one more example, which we'll do now, but it does involve some more formatting, so we'll get there. Thank you, Leila, for picking up my inability to multiply two numbers. I have fixed it. But these two rules that we have here, guys, are going to be your bread and butter for calculus, right? If you can apply these two rules, you're good. You will find the derivative. And all it is a shortcut to first principle. Rather than having to do first principle every single time you need a derivative, apply your rule, off you go. You only use first principle if you're asked to do so. Right, does anyone have any questions about any of these rules, formatting, notation, anything like that? Right, I'm going to assume we're good. Obviously, if you do have questions, you just let me know. But let's have a look at this last example, example 6, to see how we would now deal with proper notation. We'll see if we get to example 7. I'm not sure if we will, but we'll see. How we deal with proper notation as well as correct formatting. Okay, so we can see here that we've been asked the derivative of this situation. But my issue here is the formatting. I cannot yet find the derivative until my format is correct. What that means is I need to keep this derivative of x and my square brackets. I can only drop that when I start doing the derivative. So let's deal with the situation. Now, we've actually already dealt with this cube root of 27x to the power 9. So we do know what that is. This would be 3x to the power 3. And then because this was all 2 over 3x to the power 3, my correct format would be 2 over 3x to the power negative 3. So we did actually do this in the formatting examples earlier. So we know what it should be, and we can write that into our bracket. Right, now only that my format is correct can I start doing the derivative. So you can drop the d of x in the square brackets, and we now apply our derivative rules. Now, again, I am just too lazy to grab a calculator at this point, so we're going to just do this by hand. You use a calculator. Please don't do the multiplication in your head. Just use a calculator. 2 over 3 times negative 3, I don't know why I'm panicking. This is a nice, easy one, is going to be negative 2. And then we subtract 1 from our exponent, giving me x to the power negative 4. You found the derivative. So format, always double check, which is what we did in this example 5. Remember, I said double check your format. Everything's good, cool, we move on. And once your format is correct, you can then find your derivative. If you need to sort out your format, you keep the notation for d of x notation. And once you find the derivative, you drop it. Okay, we do have time for example 7, which is awesome. Let's just do this. Okay. Derivative of y over, or in terms of x, nice and easy. Again, we need to check our formatting. So this is the thing I have an issue with. Root of x is actually the basic one that we use as our rule. And so, Kanye, I do see your question. I'll get you now. Is the basic one that we use for our rule. This is an exponent of 1. So according to our rule, we would say x to the power 1 divided by the root, which is 2. So this is actually just x to the power half. Right, Kani, yes, you are more than welcome to leave your exponent as a negative. I know we always say leave it in positive. So if you do want to go a step further and say negative 2 over x to the power positive 4, that is absolutely fine. But in this context, we don't mark you down for a negative exponent. We will absolutely give you 4 marks for negative exponents or leaving your answer in a negative exponent. If it was like an exponent question where you were simplifying an exponential expression in the section of exponents, then yes, you would need to leave your answer with a positive exponent. But in calculus, it's fine because that's just one step that is not really necessary. All right, but if we have a look at example 7 here, what we are able to now do, oh, golly, Miss Molly, is we're now able to find the derivative. So we'll fix our format first. Y is equal to 3. I don't know why that 3 was so small. Let's try that again. 3x to the negative 4. We need to bring it up. Minus 2x to the power half. And then we apply our rules. Now we can apply our derivative or introduce our derivative notation. Minus 4 times 3 is negative 12. x to the power minus 5 because we subtract 1. Negative 2 times a half is a negative 1. A half minus 1 is a negative a half. So negative x to the power negative a half. Again, if you want to fix those negative exponents, go for it. But in calculus, honestly, we don't care. We will give you full marks. All right, but that is the derivative rules. That's it. We are going to do more of this on Monday. So if you still feel you need more practice, don't stress. You will do more practice, or we will do more practice. But that's it. Right, so take your screenshots. There is your quiz link in the chat. Please do go and try. Give it your best shot. What I'm actually going to do quickly before you get too excited about screenshots is do this. If you want to give those a try, you are more than welcome to.